Hello, this is going to be your Chapter 1 PowerPoint presentation because of our second snow day in as many weeks. It will be relatively long, so you may want to pause in some spots. You also may want to go back through the PowerPoint without the narration because there's going to be some slides that we're not going to spend as much time on. The really important pieces are going to be the definitions that we're going to look at in 1.1 and 1.2. The types of measurement levels that we'll look at in 1.3, and the ways to collect sample data in 1.5. There's lots of other information in here, but it's mostly going to be background information. It's going to be the type of stuff moving forward that you're going to kind of assume has been addressed. You're going to assume that the people who are presenting these studies don't have any kind of secret ulterior motives. You're going to assume that the data is actually a representative sample. But when you're watching the news or you're reading papers, these are the types of things that you'll want to think about, like what we see in 1.4, to make sure that you're not being duped. Let's get started. Like I said, there's a lot of definitions. Well, first, we're going to want to define what statistics actually is. It's about studying a large group of people, and we're going to collect data through polls, studies, surveys, lots of different ways. Essentially, it is the science of planning the study and/or experiment, obtaining the data, organizing, summarizing, presenting, analyzing, interpreting, and drawing conclusions based on that data. Statistics is not just the percent that they splash in the title of the study, right? It's not just the data that you get. It is the whole package. The data that you could collect could be a number, and it most likely will be a number, and it certainly will be for our class, but it doesn't have to be. The data you collect could be yes/no answers. It could be a survey response like you guys did on the first day of class where it's agree or disagree. It could be genders, it could be ice cream flavors, it could be what's your dog's name, it could be anything at all. It does not need to be a number. You're collecting data so that you can get an idea about an overall population. The population is the complete set of individuals that you're studying. So again, this doesn't have to be like a population of a city or a state or a country. It could be a population of all the students at Mitchell Community College, like you're going to look at in your first lab. It could be the everything, quote unquote, of whatever fits that definition. All high school football players, all the people who run Publix supermarkets that I'm impatiently waiting for my Publix to open out in Denver, right? So it doesn't have to be this big, massive thing. If you can get information from every single member of a population, we consider that a census, right? That's like our U.S. Census that comes up in every 10 years where we kind of pretend that we get everybody. We know we really don't get every single person, but we get enough. If you can talk to the entire population and get their data, then the data that you've collected represents a census. But more than likely, you're not going to be able to get to talk to everybody, even if your sample or your population is what you would consider a more manageable population, like all the students at a school or all the people who shop at one particular store or live on one road. So you're going to want to get a small sub-sample, and that's going to be a sub-collection of members from that population. Now, it's really important that you get a good sample, so we'll talk a lot about that in 1.5. The sample data has to be collected the right way. Ideally, random selection, although it's not always just a random selection, as you'll see later on in the PowerPoint. But if you screw it up, whoops, wrong direction, if you screw up the data, the sample data, right, the type of sample that you're collecting or the type of data that you're collecting, there's nothing that you can do with it. You just got to toss it and start over. So the sample that you choose is critically important. You have to make sure the sample is selected properly. If not, you can kind of like, dupe a lot of people. Say you did one thing and actually did another, or, collect sample data and then you don't say what the sample was or where you got it from, and then you just make some decisions based on stuff that's really not true. So how do you know if you've been lied to? And this is a big thing now, right? Now in the world of allegedly fake news, and there's lots of big data out there. Big data is a great field to go into because you're going to probably make quite a bit of money, and there's lots of degrees online for it. But there's things that you want to consider and can easily consider even if you're not a statistician or in some kind of MBA program. You want to think about the context, the source, the sampling method used to collect the data, and then the conclusions that they're presenting, and the practical implications of those things, right? Because we can find out lots of, maybe interesting to you or somebody else conclusions, but that doesn't mean you can actually do anything with them. So context. What do the values represent? Where did the data come from? Why were they collected? That's not where they were collected from, but why did you collect it? Sometimes even how did you collect it, right? Did these people know that you were tapping all of their phone calls? You got to really understand that context to really understand if the procedure was on the up and up, and if even what they did to analyze the data can be done that way. Source. This one's kind of an obvious one, right? If Pepsi does a survey asking everybody, what your favorite soda is, and then magically everybody says Pepsi, you go, you might be a little biased there. So is it objective or is it biased? Is there an incentive to distort the data because of some kind of self-serving position? We see this a lot in the drug companies. It's kind of I believe the correct use of the term would be ironic, is that they actually tend to do their studies all the right way, but they always seem to get what they want at the same time. There's a great TED Talks about that. Is there something to gain or lose if you distort the results? And sometimes this is really hard to figure out the source of the data. So you really want to dig a little bit deeper than just kind of reading who published it. You may want to see who funded it, where it was, go to the footnotes to see who else may be involved. Sometimes it's harder to dig up than you might think. We've talked about the sampling method a little bit, and you'll hear me talk about that a lot. The method that you choose to get the data is huge, and one of the big red flags is a voluntary response. Now this is not like an opt-out, opt-in kind of thing where, like on the first day of class, I asked if you wouldn't mind if I collected your data and you gave me a yes or a no. That's not quite voluntary response. Voluntary response is you're watching the news and they're like, hey, call up and tell us what you think, right? So there's no weeding out, there's no reason for who responds or who doesn't. Voluntary is just like you decide that you want to be involved in this and you put yourself in, or you duck out. These tend not to be valid, as you could imagine, because they're going to be super biased. There's a way better ways to kind of get to collect data. Conclusions, and this is a little sneaky. One, of course, you want to make statements that are clear because you want people to understand what you're saying. You don't want them to misinterpret it. But you also don't want to make statements that are not justified by the particular statistical analysis that you're doing. If I'm running a study, let's talk about the one that I'm doing about course grades, I can't then just kind of weave into my conclusions, oh, I noticed all the students came early to class. I think this is how we can improve punctuality. That is just something out of left field that I cannot just pull extra findings in and make a conclusion based on the data about that. Now, if you do read any studies, there tend to be sections at the end that says like further implications or areas for future study where you say, hey, we kind of saw this, but we weren't particularly looking at any one thing, and this might be something that people in the future might also want to consider, but you don't wrap that up into the conclusions that you're offering. Of course, there's practical implications. You may find something to be statistically significant, meaning that it happens outside of just random chance, the usual probability of whatever it is that you're studying. But that doesn't mean that you might be actually able to do it. An example that may or may not be helpful. For example, if you can predict where the little ball is going to land on a roulette wheel, right? The thing that you spin it around, it's got red and black numbers and the ball spins around. Like theoretically, you can predict where the ball is going to land if you know how fast the thing's spinning and the speed of which and the direction that the ball was pushed. But you have to measure so precisely that it's not practical, because one little tiny, hundredth of a millimeter and the thing's shooting off a different direction. It doesn't have to be quite that intense. It could be that you find diet A, you lose 2 more pounds on diet A than on diet B. But was this a year-long study? Who cares about 2 pounds? You lose 2 pounds in like a week. So that may not be something that's practical. Statistical significance, I talked about it on the other slide. This is when something happens outside of just the the probability of it happening, like flipping a coin. It's 50% chance that it's going to be heads, 50% chance it's going to be tails. So if you flip a coin 100 times, you probably are not going to get 50 heads and 50 tails, but if you get 60 heads and 40 tails, is that unusual? Probably not. That's probably going to still be in the realm of being close enough to being 50-50. Now, if you flip the coin 100 times and you get like 80 heads and 20 tails, that's pretty strange. That's a statistically significant result. That's very different than what you would expect to get theoretically. We'll talk a lot about this in the probability unit. Types of data. There's going to be some definitions in here that you're going to want to make sure that you know for your first test. One of them is parameter. Parameter is a numerical measurement describing a characteristic of a population. So you're actually able to talk to all of the people in the population, and you dig up some kind of number, and you say, for example, on the bottom there's 100 senators. We talked to all 100 senators, and we said, are you Republican or Democrat? And 55% are Republican. And that 55% is a parameter because it is representative of an entire population. And that's pretty close to where we are now. Actually, I think it's 52-48, but it's pretty close to being half and half. Now, this is not called parameter methods 1, right? This is statistical method 1s, because most of the time you're talking about a stat, which is a numerical measurement from a sample. So I can't talk to maybe all of the people of the House of Reps, because I want to say there's like 435 or 485, something like that, representatives in the House. You're probably not going to get to them all, but maybe you can get to like 200 or 250 or something like that, and that would be a sample of the representatives that are in the House, and not a population. This is a pretty famous example on the bottom. Literary Digest, now called Reader's Digest. They polled 2.3 million adults, and 57% said they vote for Alf Landon. You may or may not be real up on your history, but you probably know there was no President Landon. That 57% is a statistic because they only talk to the people who happen to be reading Literary Digest. And 1936, there was no Twitter polls. This was like there was a little card. You had to go get a stamp and write down what you wanted and then mail it in, and then somebody counted it. So it's pretty impressive. They even got 2.3 million results, honestly, back then. That's a lot of work to say who you're going to vote for. But that 57% would be a statistic, because that's not all the people who voted in the U.S. Those are just the people who were reading Reader's Digest and were patient enough to mail in their information. We can talk about numbers like we just did with the 55% or the 2.3 million people. Quantitative data is numerical data where the number is the measurement. So you want to think about quantity. So numbers of jobs created, gallons of water used, heights, weights, test scores. The thing that the data you collect, the data is a number that represents some kind of measurement. Not like numbers on a jersey, like, hey, I'm player number, my jersey number is 3. That's not quantitative. That would be a label because you're not like the third person to be selected for the team. It's just like you picked it. It's no measurement of your worth as a player. It's just whatever you pick. Now, quantitative data, numbers that are used to measure something, could be discrete or continuous. And the definition in the textbook, while accurate, is a little bit more mathy than we need. And Abby's going to start barking, so you're probably going to hear some dogs barking. I'm going to pause you for a second. Okay, we're back. I think the barking frenzy has ended. A bird had the nerve to fly by the window. Unacceptable. And they told that bird what they thought about that. But back to discrete and continuous data. So the true definitions in the book result when a number of possible values is either finite number or a countable number, which really means nothing to you, at least not in the way it does to somebody who studies like set theory and math. What you want to think when you ask yourself, hey, is this number discrete? I want you to ask yourself, can I have half? Can you have half a job? No, even a part-time job is a job, right? You don't say I have 2.5 jobs if you work 2 jobs in a part-time gig. You don't say, if you have 3 kids and one's really short, you don't say 2.5 kids. You have to have 3 whole kids. I have 3 dogs. One's really small. I don't have 2.5. I got 3. If you cannot have half, then it is discrete. If you can have half, like gallons of water, you can have 2.5 gallons of water that you use. You can put 4.5 gallons in your car. You can be 72 1/3 inches tall, right? If you can have a portion, if you can have half of something, then that number is continuous. They'll say that it is infinite and have any possible values in the textbook, which is true, but it's a bigger infinity than the discrete values, which in stats we don't really care about. You may not have a number. You may have something like male, female, Democrat or Republican, right? A political party. You might say, what town do you live in? If the thing that you're collecting is not a number, it's like it's a label, then that's qualitative. And that's Penny. She's done. She saw nothing. The little one's a little crazy. Qualitative data cannot be discrete or continuous. Only numbers can be discrete or continuous. So I can't say male and female and then say that it's discrete because like you can't have half a female or something like that. Now you can say I talked to 100 females and 100 males, and so you can't talk to 99.5, and the number of people that you spoke to has to be discrete. But we're specifically looking at the data that you get. So the answer you write down when you ask your question, the thing that you write down, if that's a number, that's quantitative. If it's not a number, then it's qualitative. There's another way to look at specifically I wanted to say specifically quantitative numbers, but that's not necessarily true. It will most likely be quantitative. But we can talk about a level of measurement, and it talks about how much you can find out about not just the data in general, but individual pieces. There's nominal, ordinal, interval, and ratio, and that is an increasing order of information that you would get. So nominal is going to be data that cannot be organized in like a scheme, like a low to high. There's no ranking, if you will. So you can say yes, no, undecided. You can ask people their names of the town that they live in, and you can maybe put it in alphabetical order. But the scheme that you rank them in, that ordering scheme, isn't a rank of like, hey, this is better than that, or this is further away than the other. It's just like the order that you've decided to organize them. I always think about it from the no, so there's no ordering scheme here. Ordinal, you may not be surprised, is that there is an order. So course letter grades are a great example. You got A, B, C, D, F. You got the Likert scale that we looked at the other day, like strongly agree, disagree. But you know that like an A is better than a B, but you don't know by how much because it represents a broader class. So an A could be a 91, it could be a 99. So if I got an A and you get a B, yeah, I got a higher letter grade than you, but I don't know by how much. It could be by a point. It could be that you got an 89 and I got a 90. So when you can't tell the difference between those two things, then it's ordinal, but you know one's better than the other. Like strongly agree is better than agree. But what do you mean by strongly? What intensity level is that? You don't know. If you do know, that's interval. So if I say what year you were born, I can find out how many years older I am than you. I can rank them. I can put them in a meaningful order, and I can find out the difference between them. But the problem is that there's no natural or meaningful zero, sometimes they'll say. So like BMI, body mass index, you don't have a zero or else you got no body, right? That you can't have a zero BMI. Life expectancy, you wouldn't say zero because that's not meaningful, then that there was no life, I mean, there was nothing there. So it's not just about being able to have a zero, that it also represents something. In education, we have this with test scores. So if you don't show up for a test, I got to put in a zero. Well, but does that mean that you got a zero, or that I'm giving you a zero because you weren't there, right? If I were to submit that data to somebody and they see a zero for a chapter 1, 2, 3 test, they don't know if that means they literally got every question wrong, which is unlikely, or they just didn't take the test. Last one, it's what you might think. It's that you do have a meaningful zero, and that is a ratio. So you can rank them, you can tell the difference between them, and you know that the zero means something. Income. If you have zero income, then you earn, and I'm talking about like the accounting definition of income, like I worked and somebody paid me money, right? So no zero income, no taxable job. And some of these are harder than you might think, like a housing price. Somebody could give you a house for $0. I guess you could say, you probably wouldn't say you paid $0, or else actually taxable, if we're talking about counting, you probably would say you got $0, you'd be gifted. Ratio and interval are sometimes are hard to talk about, which is which. It's a little bit easier if you're talking about like medical studies, right? If you get 0 milligrams, then you didn't get the drug. It's not that we gave you 0 and somehow it wasn't taken or something like that. So you have nominal, only categories, you can't rank them. There's no ranking. Ordinal, you can rank them, but you can't really tell the difference between the two of them. Interval, you can tell the difference, but there's no meaningful zero. They'll say a natural zero. Another good example of this is temperature, pretending there's no such thing as Kelvin, right? You can have 0, but who cares, because then you can just go negative. Ratio, there's a difference, and there's a natural zero, like you go to the store to buy stuff and you spend $0, so you probably didn't buy anything. So now we're going to look at 1.4, which is critical thinking. It's not quite as imperative as, say, the stuff that we talked about in 1.3 that we'll talk about in 1.5. This is the kind of stuff that we're going to see a little bit of this again in chapter 2 when we talk about bad graphs, but it's also the kind of stuff that you hope that is being accounted for, like when you're reading the journal article about the study. How do you know what's going on? You want to, of course, look at that context, that source, the method, conclusions, and the practical implications. But there are some misuses. This is a real book. It's a pretty old book now. It's actually old when I got it. It's in my office somewhere. But there are some pretty common examples of a misuse of statistics. Sometimes, people just lie. Evil intent. They know they doctored up the data, and they're going to just roll it out anyway because they want to convince you of something else. I would say you see a lot of distorted data. Evil intent might be a little bit much, but there's definitely a lot of times when I read things, I say, well, yes, but, that's not false, but it's not 100% true either. Now, sometimes these errors are just people that didn't know any better. Maybe they just made a mistake and they didn't even realize they made a mistake. They didn't know that they ran something wrong. They didn't realize that something was left out. So it's not always that they're super shady. Speaking of shady, you got some shady graphs. Graphs are a big deal, and we'll talk a lot about graphs in Chapter 2. Your graph must have a few features to make sure that you're not making the data look, worse or better than it really is. So on the left here, I got the good graph, right? It starts at 0. It goes up by an interval that's the same each time. The actual space, like the font space between these guys, are the same. The axes are labeled. And a lot of times you'll see this with histograms, is that on top of the bars, they'll actually put the number because it's kind of hard to tell. But you look at the difference between just shy of 33,000 and just over 30,000, that doesn't look so bad. That looks a lot better than this graph that started at 30,000 and then went up only by 1,000. It's not really a problem that they went by 1,000. It's also not really a problem that they have this huge gap. The issue is that they didn't start at 0. So it blows up this difference between here. Had this been from 0, they probably wouldn't went by thousands because they would have had 33 little dashes. But even if they did, it would have not been this huge gap in between here. So make sure that you're starting at 0 and everything's labeled. You don't want to take stuff that is not a picture and make it into a picture. So this is daily oil consumption in millions. Good graph. They turned it into a pictograph. This is the reason political cartoons love to use pictographs. It really over-exaggerates. I mean, not just exaggerate, like it super exaggerates the differences between things. And we'll talk specifically about how that does that in Chapter 2. But it has to do with, if you give something a shape, you're not just giving it a height anymore, you're also giving it a width, you're possibly giving it a depth. And so now something that was just a one-dimensional thing looks like it's 3 times or 9 times or 64 times worse, depending on what measurement you're using, than it really is. Bad samples. There's a lot of bad samples in the world. That's probably the biggest lesson you learn when you start reading studies. Voluntary response sample, we already talked about that, why that's bad. But also, you need to make sure that the sample is a good a fair representation of the population that you're studying, and that it's balanced. So voluntary response is always a bad thing. But even if you do things in the way that we'll look at in the next section, you may also wind up with a bad sample. So you got to check these things. Correlation and causality. At the bottom here, you'll see correlation does not imply causality. Just because there's a relationship doesn't mean one causes one. A very, very famous one is that SAT scores and household income appeared to be linked. The higher the SAT score, the higher household income that student seems to have, or I guess I really should go the other way around. The higher the household income, the higher the student seems to score on the SAT. Now, this is a very high correlation, and people don't even argue against this kind of thing anymore. But it's not because you have a high household income that you naturally just happen to become, get a high SAT score, and that's certainly not the only way, but there is a relationship here. And so this is a good way to look at what factors impact other factors. Not that they're inherently linked, but there's a relationship. Now, there's lots of funny ones that you can see all the way that we'll talk about in Chapter 10, like the correlation between ice cream sales and drownings. Well, when you eat a lot of ice cream in the summer, when you swim, not a lot of people swimming in the dead of winter and unfortunately drowning. So it's not that if you eat ice cream, you're going to forget how to swim. It's like a time of year type of thing. There's lots of those types of examples. Small samples. This one usually is not what gets us in the world of quantitative research. It's usually qualitative research. But you don't want to make decision based on 3 people or 5 people or 10 people, or like those old commercials where it said like 3 out of 5 doctors recommend pick your favorite drug. You're really hoping they didn't talk to just 5 people. But these types of things happen where especially in the world of qualitative research, where you can't have hour-long interviews with 1,000 people. So maybe you only have 20 people, and then all of a sudden now you want to make a decision based on 20 people and roll that out nationwide. That could be an issue. Percentages, I tell most of my classes, if people talk to you in percents, you should be leery. Most people don't understand percents, how to use them, how to calculate them, what they mean. If you have 100% of something, that means it was all of it. You took it all. So you can't have 110% of, you can't take 110% of something. If you've improved 100%, are you perfect? No. Improve is just a percent of increase. So like 100% increase means that it doubled. I took 100% of what I had and added in. So if I had my investment of $100, well, let me say $200 improved 100%, I now have $400. Doubled. Loaded questions. Wording is very important because using certain words is going to invoke certain emotions and different emotions to different people. So you don't want to load your question to really kind of either get people upset or try to get them to lean in another direction. So one example is too little money being spent on welfare versus too little money being spent on assistance for the poor. Well, yeah, welfare is a dirty word. Nobody says welfare anymore. If you say welfare, you hear somebody say that, they're trying to get you worked up. So nobody is going to agree to that. Results 19%. Nobody's going to say, oh, too little money. But if you say what it really is, assistance for the poor, then all of a sudden 63% of people say, hey, we're not helping enough people. And so this is something that happens quite a bit. You can watch the news stations and you may feel like you're living in two different worlds because of how they word things. This debate.org, don't be fooled by the org. It's not scientific. It's a kind of a shady site, but here in the links is a link to an NPR story about a very similar thing. But I really like the shady site because they asked that question, should welfare spending be reduced? And everybody said yes, 80% yes, we're giving them too much money. Don't read the comments because they're rude. Now, even though the site itself is lousy, they asked this question two different ways. And you know from yourself, you go to the same sites all the time. So the people who took this particular question, there's a good chance that they also answered the other ones, or at least it's a very similar population, right? So if I change the wording, should the government help the poor? Well, of course the government people should help the poor people. 61% say yes. They just said welfare. No. Should U.S. government increase social services for the poor? Really should just say social services. 52% said yes. So that's a big difference from 80% of people saying, no, you're on your own. All about wording. All about wording. Order of a question is a big thing. The red link will bring you to this actual particular study. This is a real thing. Now, on top of the order of the question here, this is not a great question because it's kind of hard to follow. But would you say traffic contributes more or less to air pollution than industry? When traffic was listed first here, then it was 45% said, yeah, traffic, and then only 27% said industry. But when they reversed it and they said, would you say industry contributes more or less to air pollution than traffic, then they said industry. So everybody's kind of done something like this where people are reading you off a list of things and you're just trying to remember it all and you just kind of go with the first and the last thing you heard. Like when they read you off the salad dressings at a restaurant, they always do it at like Mach 1. But that's a real thing. And also this question is not really fantastic. It's not a great question, the way that it's worded. Non-response. Dealing with non-response is actually a big thing in statistics, and there's a way to deal with that. But there's lots of reasons why you may not have a response, and it could just be that people didn't want to talk to you. But that really throws off your data, for you to get an idea of the pulse of the people that you're trying to study. Because people who take the time to talk to pollsters and, fill out little cards and put a stamp on it, like the Literary Digest people, they have a very different view of the world than those who don't do those types of things. Now, why they have a different view of the world could be a number of different reasons. I teach, so I kind of have a weird schedule, and I was always surprised how many people would come through the neighborhood during the day, asking questions and trying to sell you things. And I was like, oh, who do they expect to be home? So, because so much of the world works 9 to 5. So if you're home, you're like maybe a soccer mom who doesn't work outside of the home. Maybe you're a student or a teacher like myself where you kind of have this cushy schedule or a weird schedule. But you could also be like my brother who always worked third shift and probably would not have been too thrilled at somebody knocking on his door at noon, waking up in the middle of his sleep cycle to try to sell him like, termite service or something like that. So why you don't get that kind of response back could be a variety of different reasons, but it could really throw off what's going on as a whole. And so that missing data can really change the results. It could be also missing data. People drop out for unrelated reasons. It could be that people lie. Like we know people tend to lie about their incomes and their ages and their heights and just weird things that people lie about. We know the U.S. Census is missing people. Right? It's hard to find all the homeless people or get people to get back to you about certain things. So it's really tough to really account for everything. You can maybe have a self-interest study where people want to promote their own thing. I actually read a self-study, not a self-interest study, but a self-study, and you know it when you read it, kind of a thing, where you're like, this is not scientific. This is like somebody's study diary. You kind of get the feel that something is not really whole. You also want to be pretty leery of precise numbers. Precise numbers don't necessarily mean they're more accurate. Actually, when I hear people say stuff like 87.23% of blah, 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 I think, oh, there's no way that's 100% accurate, It's very hard to get precise figures. It's hard to get precise measurements, whether you're talking about, feet and inches or just what's going on with people in general. So if you see something that's super precise, unless it's coming like from NASA, I would maybe be a little leery of it. And of course, there's deliberate distortion that we talked about in the one, right? This is your evil intent. Sometimes people just do it on purpose, and sometimes they don't know, and sometimes people figure it out and then they roll with it anyway, right? So they might try to sway your opinion. And these are the types of things that you read. Like I said, you read, well, yes, but what about this? Or that's not really 100%, or you're leaving out something else. So that's deliberate distortion. So you may want to take a little pause here for a couple of minutes because we're going to get into collecting sample data and the different types of samples. When we come back, when the snow melts next week, we're going to do a little activity about identifying different types of samples, and then we're going to do our lab. So let's look at how to find different types of samples. Like we said, it matters. If you screw up the sample, you just wasted your time. The data might be fantastic, but it's not going to tell you what you want. So you want to make sure that you get a good sample and that you're getting that sample in the most appropriate way. Usually the kind of like crown jewel of samples is a simple random sample. Now there's random. We'll talk about simple random. There's systematic, there's convenience, there's stratified, there's cluster, and then there's also something called multi-staging. We're going to kind of roll that into stratified, but if you read studies, you'll see a lot of multi-staging because it's really hard to get a good balanced representative sample without kind of doing more than one thing. So let's talk about random, and then we'll talk about simple random. So the big difference between the two is random is that each individual member of the population has an equal chance of being selected. So think Powerball, right? You got all the little numbers. There's 1 through 60, I think, and every little ping pong is the same size, and every little number is on one ping pong, and every little number has a 1 in 60 chance of popping up. That's individual member is, there's not like 2 number 3 ping pong balls, and there's not one giant like number 68 or 58 being this big ping pong that you feel that one first or something like that. That's a random sample. Now, if you were to Google the difference between a random sample and a simple random sample, a lot of people screw this up. A lot of what you're going to hear is like simple, random sample, like a really easy way to do a random sample. Like you write everybody's name on a piece of paper and you put it in the hat and then you pick out however many you want. That is a random sample. However, it may not be a simple random sample. A simple random sample is that every possible sample size of size n, right? So I want to talk to 10 people, I want to talk to 100 people, I want to measure 20 distances. Each one of those sample sizes has the same chance of being chosen. And the size of the n matters. So here's an example. Let's say you got 50 boys and 50 girls, and you want to choose 10 at random. Now, every boy's got a 1 in 5 chance, and every girl has a 1 in 5 chance. So if I was to split this up and say I'm going to take 10 out of the 50 and 10 out of the 50 boys, and then separately do 10 out of the 50 girls, that's not random because they're in 2 different groups. So if they were all slopped in there together, like 50 boys, 50 girls, you just shook them all up, they're all in one spot, and you're going to pull out 20, then yes, that would be a random sample. It would also be a simple random sample if they were all in together, because the chance of me pulling out 20 girls is the same as me pulling out the chance of 20 boys, right? Everybody has a 1 in 50 or 1 in 100 chance of being selected. So yes, I can think about this as a random sample, or even maybe 2 random samples if I have them split, but neither one of them are going to be, the split one is not going to be a simple random, because I can't, if I'm picking 10 out of the 50 boys and 10 out of the 50 girls, I can't pick 20 girls. But if I had them all scooted in together, then I could pick 20 girls. So what you want to think about is, if you're a simple random sample, you are concerned about the groups, but you're not going to split up the groups first. It's like you're going to put everybody in a random sample and pull it out, and then think about, like, hey, did all of the different ways that I can group people, were all of those possible, and were they all equally possible? So if you see splits in groups, you're not going to have a simple random sample. The key is going to be like everybody is in one big group, and there's the same number of things in each group. So like you have a high school, you got freshmen, sophomore, junior, seniors, and you want to talk to 100 students. If you put them all in together, you got all the kids in like a database, and you pull out 100 names. Can I have is that a random sample? Totally, because everybody's in there together. But if I'm talking about specifically freshman, sophomore, junior, senior, and I want everybody to have the same, possibility of being selected, like can I have 25 freshmen, 25 of each one, or can I have 50 freshmen and 50 sophomores? Then I need the same number of students in each grade level. So everybody's in together, but the pieces that make up the together, if you were going to label them, they're the same size. If you're confused, don't feel bad, because most of the internet is. It's difficult to explain. Most things are not flat random, and they're certainly not SRS, because it's hard to get a good SRS. They're systematic, and they will say something like random systematic, which sounds kind of silly, but it's kind of like the random where everybody's in together, and then you randomly start in one given spot. You can start at 1, or you can start someplace else, and then you go to every kth or nth element. So here I started at 2, and I'm going to take every third one. So I have 2, 1, 2, 3 in the bucket, 1, 2, 3 in the bucket, right? So that's systematic. So this is a quality assurance type thing where you're going to pull every 100th computer off the line, or you're going to review every 1,000th tax return or something like that. Convenience gets confused with random a whole lot. Convenience will feel random to you, the surveyor, but it's not to the person who's being asked. So I have this girl here hanging out the window yelling inappropriate questions to this guy walking the dog, right? This girl had no idea who was going to walk by, but he did. He knew he was going to be there. He meant to walk by there. So convenience sample is like when you read it and you're like, geez, like that's kind of lazy. Like you just hung out there and you waited to see, or you just, see what happened. That's convenience. You just set up camp somewhere and you see who's going to come by. Now, sometimes these convenience samples take a life of their own. We didn't hear a lot about it in the past election cycle, but in the previous ones, we would hear a lot about Walmart moms, right? So pollsters would just hang out in front of Walmart and ask people what they thought. Well, if you hang out in front of Walmart, you're going to get one group of the population. Now, it's certainly a growing part of the population since so many people shop there. But if you were to hang out, say, in front of Whole Foods, you're probably going to get a different idea of whatever it is that you're studying than what's at Walmart. Or if you are standing outside of Concord Mills asking questions, you're probably getting a different idea than what if you're standing outside of South Park, right? So you're going to kind of space people out, but also the time of day, kind of like the pollster question. You know, if you're there at noon, you don't know who's coming. That's just a convenience sample. Stratified. All right, so here's your groups. You break them up into groups, into categories, and then you pick from each category, and notice by the highlighting, it does not need to be the same amount. So I split this up into Republicans and Democrats. I talked to 3 Democrats. I talked to 4 Republicans. A lot of times it's the same amount, but you may want to particularly take the same percentage that represents the population. So before we had, I think it was 55, right? They said there was 55% were Republicans, which means 45 would have to be Democrat. So you may want to split that up and say, well, I'm going to talk to 6 Republicans and I want to talk to 4 Democrats because that's about 60%, 40%, right? Or you could say, I just want to talk to every 3rd person in this group, or, you know, but there's 2 groups. You're going to do 2 things. You're going to break them up into a strata and then pick a few from each strata. That's different than cluster, where you break everything up into groups, but then you're going to kind of randomly select a whole group. So think of kind of like what we have here for counties. I have these precincts. There are, looks like 32. I'm going to kind of cut them all out, if you will, and then I'm going to pick a number out of a hat and say, all right, I'm going to talk to these 3. So I'm going to talk to everybody in 5, 16, and 28. We got 100 counties here in North Carolina. Imagine those names were all written on a piece of paper and you put them in. And then you pulled out 4, and you might say, all right, I'm going to talk to everybody in Iredell, I'm going to talk to everybody in Alexander, and I'm going to talk to everybody in Franklin. I had to think of a 3rd one, right? And you don't talk to anybody from Mecklenburg, and you don't talk to anybody from Wake County because you didn't pull those out. So that's the difference between stratified and clustered. You do break them up into groups, but in stratified, you take a little bit from each. From cluster, you're going to talk to everybody in that one big chunk. Summary, you got random, which was certainly going to be a random, probably going to be a stratified, most likely going to be a cluster. And then non-random, certainly convenient. Systematic, sometimes they do kind of toss that into the random because what they may do is randomize the start spot with a random number generator and the jump spot with a random number generator. So I have heard, even though it sounds very strange, a systematic randomization. And you go, that doesn't seem like it would fit. And then you read it and you go, oh, that kind of makes sense. What we're going to do when we come back is make samples of all of these, of each type. Now, the sample could be for a study, or it could be for an experiment. We don't talk a lot about studies in stats. An observational study is that you're not attempting to modify anything. You're just kind of collecting data. And it's not that you don't see a lot of these. We're just not really going to talk about a lot of these. There's lots of different types that I will not ask you about. So you don't really need to know this, but there's a cross-sectional study, there's a retrospective, and there's a prospective, also called a longitudinal. We call them cohorts in education. So like, you know, the class of 2018 had a graduation rate of whatever the magic percent is, something like that. Experiment is going to be the same type of experiment you probably remember from your bio class from high school, right? So there's a treatment, and then there's a non-treatment. So there's a group that gets something, and there's a group that doesn't get something. Ideally, you want these groups to be randomly assigned and randomly selected, but you do want to make sure that these groups are similar. right? So you don't want to have everybody over 60 in one group and everybody under 50 in another group. That ain't going to work. You want to make sure that your experiments can be replicated, right? You don't want it to be a one-off, because what we'll see in chapter 5 is that you can do everything right, and sometimes the unusual things still happen, right? Most of the time the normal stuff happens, but sometimes weird stuff happens and you didn't do anything wrong. So you want to make sure that you can replicate it. So you're basically doing the experiment again. You want the sample to be big enough that you're not making decisions based on like 3 people, but you also don't want it to be big enough, so big that it can't be done again, right? You don't want a sample size of 20,000 people, because only like big pharma is going to be able to run a study with 20,000 people. You want to use blinding to cut down on the placebo effect. So placebo effect is very, very well documented and nobody disputes it. And it's going to be like, hey, one group gets the new drug and one group gets a Tic Tac. And we all know people that you tell them you're going to have side effect of dizziness, and then you give them like a Milky Way bar, and then all of a sudden they're dizzy. You know, like that's not a side effect of Milky Way. So to cut down on that, we give these 2 different groups, and we don't tell, hey, you're getting this or you're getting that. There's a single blind where just the person who's getting the pill or the placebo doesn't know what it is. Even better is a double blind. So the person receiving the medication doesn't know if it's the real thing or the Tic Tac, but also the person handing out the little cups doesn't know. So you can't like tip them off. There's all these little things that you do, you might give it away. So somebody somewhere knows, so we can study these things, but the person handing it out doesn't know. So you can't give away any kind of information. Things still go wrong. There's sampling errors, and there's ways to measure that. There's non-sampling errors because you screwed something up and you wrote 23 is 32. These things happen. Oh, there's confounding, and you see this a lot in medical experiments, but what we'll see here in our class is we won't know which category to put it in. So confounding means you got these results, but maybe there's another reason why this could have happened. So combo, placebo, confounding, expect a story. I love these like little essential oil things. And for a long time I had 8 a.m. classes. I am not a morning person. And I had heard like you get peppermint oil, it makes you feel more awake in the morning. So I go out and I get the thing and I get the peppermint oil and I would run it in the shower, and I was convinced, and still am, that these oils work. They help. I felt more energized. But here's the thing. I started that like the 2nd or 3rd semester I had an 8 a.m. class. So another real possibility is I was getting used to waking up way earlier than I actually wanted to get up. So that's a good example of confounding. Like 2 things kind of happen at the same time, and you're not sure what to attribute it to. Placebo effect, I'm going to roll that in there, is because, I believe it worked. But there's been some pretty significant studies, and this is not to debunk any kind of holistic or approach or oils or anything like that. But if you believe it, sometimes that's enough. Sometimes you get better. And placebo studies have shown this. We've even shown that like 2 sugar pills, you get better faster than if you take 1 sugar pill. It's pretty interesting stuff. But for us, we're going to say confounding is an overlap in classes. So you can't have the first class being stuff from 0 to 10 and the second being from 10 to 20. Because then if you come up with a 10, which group does it go in? That's going to be our confounding. We're going to have a clear divide. So we go from like 0 to 9, 10 to 19. Ways to avoid confounding. This is other things that you don't really need to know. The bottom one is of particular significance and matched pairs. You want to kind of match up like your Tic Tac eater and your real drug eater to make sure they're kind of similar in whatever the nature of whatever it is that you're studying is, like same age, same height, weight, that kind of thing, to compare results. We're not going to worry about any of that. But for an experiment, you want to make sure that you randomize, you replicate, and you blind, which sounds like something from a CSI show, but randomize, replicate, and blinding. That's the end of chapter 1, and there's a lot of stuff. When I see you again, we're going to take some questions, and we're going to go over this stuff, and then we're going to do our lab. And hopefully, I'll see you next week, because it's going to be beautiful out and no snow.